Greetings again from the upper atmosphere, well, out of the atmosphere, I'm in space. I wanted to do a shorter video here where we talked about something that's a bit more on the philosophical side of mathematics, but it has some influence on how we approach analyzing systems of differential equations and linear systems and the whatnot. This technically comes before in most of your reading, before the linear systems bit, but I like to introduce it here because it is just a sort of a minor point, and we're going to go crazy with some notation here. Okay, so we're talking about existence and uniqueness. This is god awful. Okay, so what I want to draw our attention to here is that I've got a vector valued function over here, so that's my system of differential equations, and we have an initial value for this set. Okay, and I want us to suppose that f, that function that describes the rate of change, that is continuously differentiable. So it's continuous, and I can take derivatives, and those derivatives are continuous, and that's great. Now, this gobbledygook of mathematics right here can be read as the following. Okay, if you have this initial value problem, and f is continuously differentiable, then there is going to be some value epsilon that you can find that's greater than 0. And with that epsilon, there is a unique function y of t. And what's special about that function y of t is that on an interval, t0 minus epsilon to t0 plus epsilon, so around where that initial condition is, okay, that the function that we've got there solves this initial value problem. Okay, now being able to prove stuff like this is beyond what I feel like doing in this class most of the time. It's not something I want to spend time on, but what it lets us know is that if I give you an initial value problem where f is essentially well behaved, then you know that there's going to be a solution, and that when you find that solution, it is the only one that can pass through that initial condition, and that's great. Without the initial condition, you have an infinite number of solutions, right, that all have a constant of integration that depend on where you start. Okay, now this has different ramifications depending on if our system is non-autonomous or autonomous. Okay, so specifically right now I want to deal with non-autonomous, and what that means is that coefficient matrix A may not be filled with constants, but each of those A, B, C, and D's could themselves be functions of time, so that the way that your state variables are evolving could itself change. Okay, so take some initial condition. We'll just go and grab it right there. We know that there exists a solution, and I'm going to draw something like this, and I argue that this is not in violation of uniqueness. Okay, the fact that I can draw the line means that, hey, there exists one, but you're like, hey, it crosses itself right there. What does that mean as far as like uniqueness is concerned? Like, I thought we couldn't have solution curves cross because then you don't know what's going on. All right, now what's special here is that notice we're in the phase space, x, y plane. Okay, if I start from my initial condition and go up to that point where there seems to be an intersection, that's a particular time. Let's go ahead and call that t1. Okay, now as you continue to progress along this curve, x and y are changing, but that's because time is marching on. So when you get back to that spot right there, it is a completely different time, some t2 value. Okay, and this is something that's can be a little mind-bending, going from one-dimensional stuff to two-dimensional stuff like systems. Hold on a second. No, we're all set on oxygen up here. Thank you. Okay, so there's not technically an overlap there. It looks like it because what we've done is we've squished this third dimension of time that should be growing out there. And in fact, if I totally abuse the space I have here, and I make a time plot, let's say for x and for y, and it doesn't necessarily have to do with what's drawn here. Let's just be creative, theater of the mind or whatever. Okay, so the top one I want as a time plot of x and the bottom one of y. I'm just going to draw some other curve there. Now, it's possible for x and y to have the same values, like if I think of it as an order pair, I've got some x and some y value, and some x and y value at a different time where those ordered pairs are the exact same. But you would never argue that what that does is violate the fact that there is a unique solution there, because they happen at different spaces and times. What we can't have is some other solution curve that corresponds to a different initial condition that passes through those curves. Notice they pass through the purple dot there. Both at the same time, you have the same ordered pair, because then that would mean that two different solution curves cross or touch, and that would be bad. Okay? So in these non-autonomous setups, a solution curve can intersect itself. Now, in autonomous, we're back to the situation where your coefficient matrix, they're all just constants. So A, B, C, and D are just some numbers. Right? And what's neat in the autonomous situation is that solutions and equilibria and the whatnot, what they do is they divide up our space, the XY plane, into different regions that we can, in some sense, consider separate and think about on their own. And this is an incredibly important point, and I want you to beat it into your head. That for autonomous situations, solution curves divide the phase plane. Okay? So what I'm going to do right here is I'm just going to draw some sort of closed orbit in orange. So let's suppose there's a solution curve that is Ouroboros, eats its own tail. Okay? What this has effectively done to the XY plane is it's created two different regions. That which is inside or enveloped by that curve, and that which is outside, or basically envelops itself, the curve or the yellow region. Okay? Now what's nice is what we need to assume is that anything that starts in the red cannot go to the yellow, and anything that starts in the yellow cannot go to the red. Because if it does, then it has to cross over that orange trajectory, and that itself would violate uniqueness, because it would be two different solutions passing through the same point in the XY plane. So if we pick an initial condition outside, it can either go off somewhere else, who knows, or it can actually like approach, get closer and closer and closer to that orange curve, but it can never hit it. Same thing can be said when we start inside there. We either have to go to some fixed point, we can't actually blow up to infinity if we start inside there, or it can kind of spiral around or do its thing and approach this orange curve which divides the two, but it cannot escape. That blue initial conditions cannot go into the red region, and the green initial conditions cannot go into the yellow region. That's an incredibly important and powerful point to existence and uniqueness in planar systems. All right? Thank you guys for watching. Go away. Okay, there we go. I hope this was informative, and I'm going to make another couple lectures with you, okay? Yes, please send more peanut butter. Yes, thank you.